So the work that I'm going to talk about was spearheaded by this wonderful graduate student, Ethan Lake, that I've had a lot of fun interacting with. And there's a paper that we put out in the archive as of a few months back. So we already heard about alternately twisted tilayer graphene in Abhay Pashupati's talk. So I'll talk about the same system. So the idea is that we take a stack of 3 layers of graphene and in such a way that the top and bottom layers are twisted by the same angle relative to the middle layer. At least that's the ideal structure. And this ideal structure is mirror symmetric for reflection above the middle layer. Again, as we heard in Abhay's talk, whether real devices, how close they are to this ideal structure is something to be determined. And hopefully Abhay and his colleagues will figure that out as the months go by. But restricting to this ideal structure, there's some theoretical work that says that this mirror symmetric structure may well be preferred energetically based on first principles calculations. And we'll see that a lot of the experimental data, the 0th order, seem to be understandable by assuming this ideal mirror symmetric structure. And so that's what I'll do throughout this talk. Later on, as the field evolves, some phenomena need explanations that rely on deviations from this ideal structure. But for now, we'll just assume that what we have is this ideal structure, and we'll see that there's a great deal that we can actually understand. So let me quickly review the single particle Hamiltonian of twisted trilayer graphene. So the top and middle layers by themselves form a twisted bilayer graphene, and so do the middle and bottom layers. So the single, if you focus on a single valley, then the hopping Hamiltonian in the top and middle block has the same structure as that of twisted bilayer graphene, and likewise for the middle and bottom block, right? So each one of these 2x2 blocks is the familiar problem of twisted bilayer graphene. So we can learn a great deal from our understanding of single particle physics of twisted bilayer graphene. Now this structure will be modified by external perpendicular displacement field and an in-plane magnetic field, which are both knobs that experimentalists use to tune the properties of this system. So at the single particle level, we can go to a basis of mirror even and mirror odd combinations of the top and bottom layer electrons, form these linear combinations. And in this basis, this 3x3 matrix that I showed earlier simplifies into 2 blocks, a 2x2 block, which decouples from this 1x1 block. And this 2x2 block represents the mirror even sector, the plus combination, the plus linear combination here. And this looks exactly the same as the standard twisted bilayer Hamiltonian, except that there's a factor of square root 2 in front of the interlayer hopping matrix elements. And this 2x2 block decouples from the mirror odd sector, which is just described by the same Hamiltonian as ordinary monolayer graphene. So this factor of square root 2 means that the magic angle for this block is increased relative to that of standard twisted bilayer graphene by a factor of square root 2. Okay, so at the single particle level, we would conclude that in this ideal device, in an ideal device, the twisted trilayer graphene is the same as twisted bilayer graphene coexisting with a monolayer graphene. Of course, this equation, I put it in quotes, is only true in the absence of interactions. Interactions will definitely couple together all the electrons in the system. And it's also modified by the presence of external perturbations that break mirror symmetry. Okay. So 2 interesting such perturbations are a perpendicular displacement field, which you can apply to this system. And theoretically, we'll describe this by a potential difference U between the top and bottom layers. And the second perturbation is an in-plane magnetic field. And the in-plane magnetic field, of course, has a Zeeman coupling to the electrons. But as we know from study of many of these Moiré materials, the orbital coupling is also potentially important. there is a reasonable amount of flux that goes through the Moiré unit cell, given that the lattice constant in plane is large. So an in-plane magnetic field shifts the momentum of the electrons in different layers relative to each other, and that gives rise to an orbital coupling. Okay, so both of these perturbations break the mirror symmetry, and they couple together the mirror even and mirror odd sectors. And the precise manner in which they couple them together is given by this Hamiltonian. So there is a V term which acts to couple together this 2x2 block with this 1x1 block. And the V term is a linear combination of this potential difference between the top and bottom layers and something that involves the vector potential associated with the orbital structure of the in-plane field. And in addition, there's the usual Zeeman coupling as well. So there's a legitimate question that one could ask oneself, and I certainly asked myself when Pablo Moiré-Twistronics started telling me about this system. Why should we bother studying twisted trilayer graphene? Isn't it just more of the same? And the answer we'll see is that indeed TTG shares several phenomena with TBG, with twisted bilayer graphene. But we'll see that some of the experimental clues that we get about the physics in TTG are easier to read and easier to interpret than in TBG, right? And in particular, the mirror symmetry of the ideal device helps disentangle different aspects of the physics that are mixed together in TBG in a very strong way. Here, even if mirror symmetry is approximately broken, it's a good enough, it's only an approximate symmetry. It's good enough that it enables us to disentangle different things that normally are tied together. So we can hope for a better understanding of TTG compared to TBG, and hope that we can learn lessons about the general physics of this class of systems, and that some of those lessons will carry over to TBG itself, right? So for all these reasons, it's worthwhile to study TTG. So let me review some of the experimental results. There's so far 3 experimental papers, 2 from Pablo Moiré-Twistronics and 1 from Philip Kim. So one of the most striking things that's found is that this system exhibits very robust superconductivity, right? So here's one of these color plots of superconductivity at hole doping between -2 and -3 Moiré filling. You see a prominent superconducting dome. Here's the resistivity data itself, and there's a fairly sharp phase transition at just over 2 Kelvin. And here's the IV curves, and the IV curves give you a very sharp, right? So it's a clear critical current at which there's an onset of voltage, and you can fit the data to Kosterlitz-Thouless theory, and it seems to work reasonably well, and so on and so forth. Right? So I think there's no question that there is superconductivity in this system. It's not one of those cases where it may be superconductivity. Here, definitely is superconducting. So there's a phase diagram that both Pablo and Philip Kim determined. I'm showing data from Pablo's paper. So you can tune the displacement field and the Moiré filling and look at where superconductivity occurs. You can also do, as these people did, study the Hall coefficient as a function of density and displacement field. And based on that information, and based further on the study of the Landau fan and its temperature dependence, from which you can extract out the effective mass, there's an overall conclusion that the experimentalists reached, which is quite interesting, and which is that the superconductivity is weakest at where there's a peak in the density of states in the system. For instance, the effective mass determined from the temperature dependence of the Landau fan increases and reaches a maximum around u equals -3, while the superconductivity itself is optimized somewhere in between 2 and 3 and gradually weakens as you approach the place where the effective mass is the biggest. Okay, and this is also broadly consistent with what Abhay was telling us earlier today, that it's hard to reconcile features of the band structure with where the superconductivity is strongest in this system. Now, if you turn on a perpendicular displacement field, it's seen in the experiments that the superconductivity is enhanced. And you see that here in this plot where you have a plot of T BKT as a function of displacement field. And clearly, T BKT is optimized not at zero displacement field, but rather at some finite displacement field. Okay. So this third paper, the most recent paper by Pablo's group, finds a very striking phenomenon when they turn on an in-plane magnetic field. So if you look at the critical at the IV curves, an in-plane magnetic field of up to 10 Tesla is not able to completely suppress the superconductivity, right? So the superconductivity survives up to this remarkably high fields of 10 Tesla, given that the BKT temperature is only about a couple of Kelvin. And this happens, this happens is also illustrated in this color plot. So at 0 Tesla, the blue region is where the superconductivity. Now, if you go out to 10 Tesla, the superconductivity shrinks, but it's not completely destroyed and survives in a thin sliver in the d nu plane. Okay, and so the behavior in in-plane field, there's many phenomena going on in in-plane field. One effect that I'll immediately point out is that we saw that a small displacement field enhances the superconductivity, while from this plot, where D is along this axis and B parallel is along the vertical axis, we see that even though a small d enhances the superconductivity, as you go up from one plane to the other, the region of superconductivity shrinks smoothly, right? So a magnetic field, a small magnetic field definitely suppresses the superconductivity, but it doesn't suppress it completely all the way out to 10 Tesla, okay? And this behavior is in striking contrast with what is well known in twisted bilayer graphene. This early data from Pablo's first paper, where you see that in twisted bilayer graphene, but in twisted trilayer graphene, there is a clear violation of the Pauli limit in the extent to which superconductivity survives to an in-plane field. So you can see that in the resistance traces here as well. As you increase the field, the superconducting downturn is hardly suppressed as the field goes out to several Tesla fields. Okay, and you can plot the Pauli violating ratio as a function of the density of the filling, and you see that the Pauli violating ratio is biggest around the optimal doping for superconductivity, which is around 2.4 or something like that. But it's non-zero even all the way out to a filling of around -3, where the superconductivity is weakened quite significantly. So even though the superconductivity, the bare TC is weak, it still manages to resist magnetic fields out to fields that are much bigger by at least a factor of 2 than the Pauli violation limit. Okay, and one of the most striking things that was found in the same experiment is that the superconductivity is actually re-entrant at optimal doping, at optimal doping and optimal displacement field. So this blue curve, this blue region, initially seems to shrink to 0, and then it reappears again. And you can see that in, say, the resistance traces here. So as you increase the field, first of all, this initial downturn of the resistivity, that downturn temperature just decreases monotonically. But if you zoom in to this narrow region and you look at where the resistance actually goes to 0, so initially it goes down, that temperature goes down, superconducting temperature, but then it comes back up again, right? So you see a clear crossing of these curves. And so that's this re-entrant TC. Okay, now then it's interesting to point out that what's actually re-entrant is not this onset temperature where the resistance first starts falling down, but rather it's the actual TC at which the linear resistance goes to 0. So this suggests that what's re-entrant is the BKT transition, while the T onset itself decreases monotonically. Okay, So anyway, so that's a summary of some of the interesting phenomena and experiments. So the questions for theory are the following, right? So we want to understand the nature of the superconducting state and perhaps ideally also the normal state. We want to understand why displacement and in-plane magnetic fields have opposite effects, though both end up breaking the mirror symmetry. We want to understand why TTG and TBG superconductors show different stabilities to in-plane magnetic fields, though they are nominally somewhat similar. And finally, how should we understand the re-entrant superconductivity? And even more finally, what lessons do we learn for twisted bilayer graphene from if we could understand all these phenomena in twisted trilayer graphene? So the strategy that I'll take in this talk that we took in this work with Ethan is that we'll take input from many different corners. We'll take input from experiments. We'll try to read what the experiments are telling us and try to form a picture of what they're telling us. And we'll combine that with some simple-minded theory. We'll take inspiration and we'll borrow results from the strong coupling theory of twisted bilayer graphene, particularly developed for the correlated insulators. We'll use the Ginzburg-Landau theory, whose structure, aspects of whose structure we can actually determine quite reliably. And the reason is that the in-plane magnetic field and the displacement field only enter by coupling together the mirror even and mirror odd sectors. So whatever Ginzburg-Landau theory describes the superconductor when D and B parallel or zero, the modification to the Ginzburg-Landau theory by these perturbations is something that we can calculate a bit more reliably than the bare Ginzburg-Landau theory itself, because these only enter by coupling together the strongly interacting mirror even sector with the almost trivial mirror odd sector. Okay. So the plan of the talk is that I'll start by talking about the normal state near nu equals plus minus 2. And we'll make an argument that the spin is polarized in opposite directions in the two valleys in the normal state. In addition, there's quite likely some sort of intervalley coherent order, but this is a dominant feature, we believe, in the normal state. And this will lead us to argue that the superconducting ground state is a mixture of triplet and singlet pairing. It's not a pure triplet, as you might naively guess. And we'll be able to discuss the effects of displacement and in-plane fields and explain the differences with twisted bilayer graphene. And I'll build the case that the re-entrant superconductivity occurs through what's known as a quantum Lifshitz transition to a finite momentum pair condensation. And the mechanism for this finite momentum pair condensation will be distinct from FFLO, but rather it occurs through this quantum Lifshitz mechanism, which involves a change in the phase stiffness of the superconductor, change the sign of the phase stiffness of the superconductor. So let's start with thinking about the normal state. Here we get an important clue from experiment. The Landau fan coming out of nu equals minus 2 was determined in both these papers, and it has this interesting feature that the degeneracy of the Landau fan is only 2, 4, 6, and so on, right? Given that there's a valley and spin degree of freedom, you might have at least expected a 4-fold degeneracy, but instead you only find a 2-fold degeneracy. So the simplest hypothesis is that you're polarizing a flavor degree of freedom. And this is something that people have suggested in this field and other Moiré materials for a long time. And the simplest kind of flavor polarization is to assume uniform Q equals 0 flavor polarization. And that's consistent with a lot of the existing theory on TBG. And it's also consistent with many experiments on TBG. So we'll just make Occam's razor demands that we just make the same assumption here for what kind of flavor polarization. So the next question is, which flavor is polarized, right? So one thing we can easily rule out is valley polarization, which is, for instance, seen in twisted bilayer graphene aligned with HPN. But here, there's no sign of broken time reversal or hysteresis, unlike in this system. And furthermore, breaking time reversal is bad for superconductivity. So for all these reasons, valley polarization is not favored in this system. A further hint as to the normal state comes from the superconductor itself. The natural assumption that to make in this problem is that the superconductor inherits the flavor polarization of the normal state. After all, the normal state is a much higher energy scale. The flavor polarization of the normal state is a much higher energy scale phenomenon. So it's natural that the superconductor will inherit whatever structure there is in the normal state. Now, spin polarization within each valley is good for the Pauli violation that the experiments see. So we then clearly have to assume that the flavor polarization is such that within each valley, the spin is polarized. But a priori, we know nothing about the relative orientation of the spins in the two valleys, right? So spins in the two valleys, a priori, could point in completely different directions, even though within a single valley, all the spins are fully polarized. Okay, so what argument can we use to fix the relative spin orientation between the two valleys? Now, microscopically, what will fix this relative spin orientation is the sign of an inter-valley Hund's coupling JH. And this was mentioned by Lena Bascones in the ABC trilayer system. But here we have a different system, and we have to ask what we know about this inter-valley Hund's coupling. So here there's a competition between the Coulomb interaction, which favors a ferromagnetic Hund's coupling, versus a phonon-induced inter-valley Hund's coupling, which favors an antiferromagnetic sign for this for JH. Now, in Moiré graphene, an estimate of this phonon-induced effect gave a magnitude that was comparable to the best estimates that are available for the Coulomb-induced JH. This means that theoretically, we don't know the sign of JH. And so we don't, purely theoretically, we don't have a strong way to fix the relative orientation of the spin between the two valleys. So in the absence of strong theoretical guidance, we'll turn again to experiments and use phenomenology to fix the sign of this relative spin orientation. Okay. Now, if we have ferromagnetic JH, then both valleys have the same spin. Then the resulting superconductor will be fully spin polarized, right? So we just have same equal spin pairing of both valleys. Now, in this case, we can ask about the structure of the superconducting order parameter. And it turns out that the order parameter manifold is SO3. It's not the regular, it's not the usual kind of superconductor, but rather it's a superconductor that's described by an SO3 order parameter. And such a superconductor has no BKT transition. A BKT transition is a feature of an XY order parameter. If you have something like a rotation matrix as an order parameter, it's known, or simple StatMech will tell you that there's no BKT transition. Now, furthermore, with this order parameter manifold, you can show that there are vortices in this order parameter with this order parameter, but those vortices only have a discrete Z2 structure. This means this has the immediate consequence, as pointed out in this paper, that the critical current of the superconductor will be 0. Okay. Now, if you look at the experimental data, it's very clear that there's a non-zero critical current at 0 temperature. Okay. So phenomenologically, this kind of superconductor is completely ruled out by the experiments. So we have to conclude, therefore, that the normal state cannot have this kind of completely ferromagnetic polarization of spin either, right? This means that phenomenologically, we rule out this ferromagnetic JH, and we therefore have to pick this antiferromagnetic JH. So the spins, we conclude that the spins point in opposite direction in the two valleys, okay? And this strongly constrains the structure of the superconducting state in TTG. So let's turn to the pairing structure of the superconductor. So the spin symmetry is already broken in the normal ground state. And the assumption is that at 0 magnetic field, the superconductor inherits the spin valley locking of the normal state. This means that the pairing involves opposite valley and opposite spin, right? Now, if you write down any pair or the pairing order parameter for this kind of given this kind of normal state, given that these two kinds of electrons that pair, the thing that you end up with is that given that spin symmetry is already broken, what you end up with is a coherent superposition of a spin triplet and spin singlet order parameter. Okay, so this order parameter manifold supports z-valued vortices and hence a BKT transition and a finite critical current at zero temperature, right? So the naive assumption of a triplet superconductor is, I think, ruled out phenomenologically, and this is the thing that can survive phenomenologically. So we do not know the orbital structure of the Cooper pair, and in writing this down, we simply assumed even parity for simplicity, but we can easily modify the story to include odd parity superconductivity. So let's discuss the effect of the in-plane field. So the Zeeman effect, due to the Zeeman effect, the only thing that will happen is that the electron spins within a pair will gradually cant to get some net magnetization along the field. So this doesn't lead to any limitation of the superconductivity. You gain Zeeman energy by the pairs adjusting their spin. So this enables a Pauli limit violation. It escapes the Pauli limit. Now let's ask about the orbital effect of the in-plane field. Now in TBG, it's known that the orbital effects of the in-plane field are important in the superconductor. They lead to effects like the direction dependent of the critical field that was discovered by Pablo's group. But TTG is different. And the difference is that due to the mirror symmetry, the dispersion, unlike in TBG, satisfies the feature that even in the presence of an in-plane field, K and minus K are degenerate. This means that the depairing mechanism of the in-plane field in TBG that exists in TBG is no longer available in TTG, and that's a consequence of this mirror symmetry. Okay. Now there will be weak orbital effects that arise from mixing of mirror even and mirror odd sectors, but the dominant effect that kills superconductivity within an in-plane field in TBG is no longer there in TTG. Okay, so both Zeeman and orbital effects of B parallel are weak in TTG, and therefore superconductivity survives well beyond the Pauli limit. And this also explains why there's a difference with TBG. Okay. So finally, let me conclude with this background addressing the surprising phenomenon of this re-entrant superconductivity near optimal TC. I pointed out that T onset is monotonic, right? But it's only T BKT that's non-monotonic. Now T BKT is controlled by the phase stiffness, while T onset is controlled by the zero temperature condensate fraction. This suggests that the re-entrant transition is associated with the suppression and re-emergence of the phase stiffness rather than with the suppression of local pairing. Okay, so if you think about the theory of phase fluctuations of the superconductor, there's some Lagrangian that describes the phase mode. It has some phase stiffness and nonlinear terms. Now, in an ordinary superconductor, this phase stiffness K is bigger than 0, but you could imagine a phase transition where you drive K to 0 and change the sign of K to a negative value. The theory will then be stabilized by these quartic derivative terms. And this kind of transition is what's known as the quantum Lifshitz transition. And when K is negative, what happens is that these quartic terms will stabilize the state where the pairing occurs at non-zero momentum, and you get a finite momentum paired state. So this finite momentum paired state, the mechanism for it is completely different from FFLO in that the pairing is not at all suppressed. What's suppressed is this phase stiffness, which goes to 0, changes sign, and then these quartic terms stabilize this finite momentum pair. So let me maybe skip this. So there's some support for the story from the Landau-Ginzburg theory that I alluded to. Maybe I'll quickly mention that if we think about the Ginzburg-Landau free energy, and ask how these parameters K, R, and U change as a function of D and B parallel, we can calculate the structure of these changes by integrating out the mirror odd fermions. which are coupled together to the mirror even fermions by these couplings, and that enables us to show. So based on the structure of what we get, we can conclude that for small u, that a small displacement field stabilizes superconductivity, while an in-plane magnetic field is capable of decreasing k to 0 before killing the condensate fraction, depending on the precise values of these parameters, and that can then help explain. It allows for the possibility of this re-entrant quantum Lifshitz transition. So let me just stop here. I won't talk about the experimental tests, and let me summarize. Let me just repeat the summary slide. Thank you.